So next we have Puneet talking about testing integration between Twitter services when he is ready. Master deck.
All right, so October 8th last year, Twitter signup was broken for almost 2 days. Stock was down 5%. How many people remember that? Yeah, so for the folks who raised their hands, that actually never happened. And this is the reason why it didn't happen. Sorry. All right, so I originally came from platform engineering and then started realizing that we had bigger problems to solve and ended up spinning up a new team called Frameworks. And one of the first things we built was this tool. And the problem we were trying to solve with this tool was that you just refactored your code. We were in the process of migrating over from a huge monolithic Ruby app to microservices-oriented architecture. So lots of opportunities to break things. And at the end of a refactor, how do you know that you haven't broken something? If you're an SRE, a site reliability engineer, and you're in DevOps, then you have an even bigger problem because you have no understanding of the code that is about to be deployed, and yet you are in the position to make the call as to whether or not a build is good enough to put out into production. And you try to mitigate that risk by canarying and doing all sorts of fun things, but eventually you want to get to continuous deploy, and that ends up being a hard problem. So our natural first line of defense comes out to be unit tests and component tests. And I personally have to make a confession. What better audience than this one to make this confession that I hate writing tests. And the reason is the following: that if you look at unit tests, it can often take you more time to write good unit tests than writing the code that's being tested. Let's say your method has 5 possible code paths, and you're interested in 100% path coverage. Then one test will get you 20% coverage. You write 5 tests, and you're done. Great. I mean, I can write 5 tests. That's not a problem. But 5 tests for every method. Then you get a bit more ambitious, and you say that I want component test coverage. And in this example, I have 5 methods in my service. So my component is a microservice, and the request path has 5 methods in it. And each method has 5 independent code paths. So this works out to about 15,000 independent code paths. Now, who here has written 15,000 tests for anything? Right. Wow. I have a lot of respect for you, sir.
But our team has billions of test cases.
Right. OK, well, kudos to you guys. But the thing to be cognizant of here is that as the complexity of the system that you're trying to test grows, the relative impact of every handwritten test is smaller and smaller. And if I take the example of one of our services in production, and I use the production cluster that's running that service just to run tests, it would take about 1,000 years for that cluster to finish running all the tests covering every single possible code paths. Meanwhile, the life cycle of that software is barely a week, because that's how long it'll be before the next version of the code will get deployed. So we need to be cognizant of the impact that we can make as complexity grows. And if you don't trust me, hopefully you trust this guy. So what's our approach to automatically trying to find regressions and figuring out whether we've broken something? Well, first we start by saying, if you look at a test, it's finding a way to trigger a behavior, right, which is providing a test input. And what better way to trigger the behavior that you're interested in than to use production traffic for microservices? So we started using production traffic to drive the behavior of undeployed code. And that basically made sure that we were exercising the code paths that were going to be eventually exercised in production. We preferred this approach to randomized testing or other kinds of testing because with those approaches, while you might get different kinds of coverage and whatnot, there are a lot of data-driven things in your code which only happen to surface when you get the right sequence of characters and whatnot that are easy to find in production traffic than randomly generated strings and things like that. So using production traffic to drive the behavior of undeployed code turned out to be a good approach. And then the second part is once you've had your interaction with the undeployed code, then you want to assert that the behavior was correct. So how do you do that? And you make the assumption that the stuff that's currently deployed in production isn't broken. Sometimes there can be the wrong assumptions, but most of the times, if production's on fire, you find out pretty soon. And if it's not, then you can assume that the stuff in production's good. But there is a problem. You're using the same request. You're sending it to the new code and to the old code, and then you're comparing the responses that are coming back from these two deployments. And in this response, you might have a lot of fields, deeply nested fields. And some of these fields might be inherently noisy. So how do you deal with them, right? Your noise could be, for example, from server-generated timestamps, because the clock is never going to be exactly the same across two different machines, and it's not the software's fault. It's just a different clock. You could have random number generators, and you may not have set the seed, in which case, again, you have another source of non-determinism. You might have live data for downstream services that you're using for both the environments. And if that downstream data is changing rapidly, then that can be yet another source of non-determinism, because you can have a write in between the two reads that the two live and undeployed versions do. So here's the big idea with Diffy, where once you have production traffic that you're driving through the Diffy proxy, it will multicast this traffic to not just to the old code and to the new code, but two versions of the old code. So in this diagram, you see a candidate at the top. This is the new code, right? The code that needs testing. The primary and secondary are two deployments of the exact same known good code, which also happens to be currently deployed in production, right? So all of these three instances are running in my isolated staging environment. Then, when the traffic hits these instances, and we get the responses back, we do a comparison between the candidate and primary. So that's a comparison between the new code and the old code, which gives us a raw set of differences, right? And then this raw set of differences has a lot of noise in it, right? And then by comparing the old code to itself, which is the comparison that's happening here between primary and secondary, we isolate all the fields that are inherently noisy. So anything that shows up as noise here between primary and secondary gets subtracted out from the raw differences, and you get a final filtered set of differences that allows you to focus in on things that you should be looking at, as opposed to trying to find a needle in a haystack. And with that, let me switch over to the demo. So as I showed you in that diagram, we need three instances. So the first one up here, running on port 9000, is my primary. The second one here, running on port 9100, is my secondary. And then my candidate is running on this port 9200, right? So let me look at my Diffy configuration. So candidate is running at 9200, great. Primary 9000, and secondary 9100, great. So let's run this. OK, so I have my Diffy instance deployed now. And not doing anything interesting, so let's send some traffic to it. And since I don't have a production traffic source, I'm just going to run a bunch of curl commands that I have in this script here. OK. So we just sent a whole bunch of traffic to this Diffy instance. It showed up in the logs here. And then you can also see that traffic being multicast to all of these service instances. So let's go back to the Diffy instance. Wow, 100% of the traffic failing, and it tells me that this endpoint's called JSON. So let's go take a look at what these differences look like. OK, dates coming out to be different, 49 seconds, 50 seconds. OK, what else is different? Names are coming out to be different. Interesting. And then timestamps are coming out to be different. So notice that it says 100% failing, 100% noise. So the 100% failing here is saying that 100% of the time, primary and candidate disagree with each other. And the 100% noise means that 100% of the time, primary and secondary disagree with each other. Now, in this sort of situation where 100% of the time, primary is disagreeing with secondary, you can be fairly confident that it's not your code's fault, right? Whereas up here in the name field, 12% of the time, primary is disagreeing with candidate, but primary and secondary are always agreeing with each other. So in this situation, you can be fairly confident that it is your code's fault, right? So using this primitive logic and some primitive statistical analysis, you can apply this auto-exclusion logic, and it automatically eliminates these other fields where the noise threshold is fairly high. And if we deep dive into one of these guys, we see that the words here in the responses, the names in the name field in the responses are capitalized here, whereas it's lowercase here. And it's capitalized here and it's lowercase here. So that's sort of a regression in my service, and I can deep dive into the response by blowing this up, and it gives me the full-blown request that was used to trigger this behavior, so I can reproduce it if I want. And it highlights these nice fields for me and tells me what's exactly different across the two. And the sort of diffing that's happening here is that it's recursively parsing the response data structure. In this case, it happens to be JSON, but we can also parse thrift responses and HTML. And do this sort of analysis at, throughout the structure of the response. That's my demo. So at this point, we can switch over to the master deck again. Right. Any questions?
Can you hit top, please? Don't know why it doesn't always stay there. How can you handle situations where production traffic contains private user data? How can you debug?
How do you handle situations where production traffic contains private user data? How can you debug? When production traffic contains private user data, for read requests, we're just able to use production backends. And the way we're sourcing traffic is by instrumenting our production cluster. And so the reads are fine, as long as they're backed with production backends. Writes are a bit more complicated, and that's work in progress. I can talk a little bit about it. So what we're doing there is not only are we recording the requests in production, but also all the interactions with the environment for that request. And so as a result of that, what you end up doing is in your test environment, you're able to replicate or dynamically mock the behavior of the environment as it was recorded in production. So that allows you to decouple the component that's being tested completely from the environment, and you can do this sort of testing in complete isolation without having any downstream dependencies.
How do you tell Diffy to ignore expected changes such as bug fixes?
Good question. We don't, and very deliberately so. The reason is that we experimented with that earlier on, and we found that giving people the ability to write exclusion logic, that you can ignore these fields, creates a blind spot, because those exclusions have a life cycle of their own. And it creates a burden of maintenance on the service owners that they have to actively maintain that list, so that in the next release they don't forget to retire the exclusions that went out in the previous release. And so the way our automatic artifact promotion process is being built is that if we don't find any regressions, we automatically promote the artifact. But if we find any regressions, we require a human to sign off on those regressions and say that, yes, these changes are fine to go into production. But from Diffy's point of view, we don't give them the responsibility to maintain a list of exclusions or anything like that.
Cool. We have time for one more. How do you mock the data backend such that the undeployed code doesn't affect it adversely while still maintaining the similarity between responses?
How do you mock the data backend such that an undeployed code doesn't affect it adversely while still maintaining similarity between responses? I'm not sure if I fully understand the question.
Basically, if you've got a backend that is part of the system under test, and your front end is taking requests, and if you're only really trying to test that front end and you don't care about some dependency that's giving you like weather information that's also applied to the tweet,
right?
How do you make it so that that isn't actually what Diffy's finding?
Right. So just for clarity, in terms of the scope of Diffy does not take ownership of deploying your downstream dependencies, and that story is left up to the user. But what we do in production, or what a lot of services do at Twitter, is that we write our custom backends or like mocks for backends for these particular reasons. So, for example, if you want to replay writes, one of the things that we're able to do, or some services are able to do, is create a mock backend which just returns the OK200 response, but actually throws the downstream write away, right? So it's not actually persisting the write, and it's not trying to propagate that change further downstream. It isolates it, and that allows you to, again, keep your component decoupled from your downstream dependencies. Happy to chat more about it afterwards.
Thank you.